Thanks a lot. I appreciate that warm introduction. It's always nice to make it back home in Seagrave. It's a place where I grew up as an amateur astronomer. Been a member here since I was 14 years old. And I know a lot of the older members. They're all old family members to me, all lifelong friends, and old-time family members. Yeah, I want to thank Steve and Kathy for getting in touch with me and asking me to come and do this talk. This past summer, actually last year, from March till October, we took on a really large project at the University of Connecticut. And I'm going to go through how all of that came about, and we'll get started here.
Can we shut the lights in the front?
Okay. That work?
Yeah.
Yes.
Okay, good. So, this talk has 127 slides. I have about 45 minutes. I want to try and pull this off. So I'm going to be flicking, but hopefully I'll dwell on some of the key points and show you some of the things that happened here. I'm going to start out with how I originally got started with UCONN. Yeah.
I'm just trying to pull this down so you can see
Okay.
everything.
Yeah. There's 8 sections to this talk. The first is how I got started working with UCONN, and then our first trip out, the inspection of the old observatory at East Road, the development of our statement of work and design improvements for the telescope, and once the work started, what we were doing, some of the fabrication and testing that had to take place along the way, and we'll get into the reassembly, and I've got what everybody loves to see, the before and after comparisons. So, and then finally, some of the rededication and first light to wrap it up with. So, moving along, this is how I got started. This is a 16-inch Cassegrain that I built. Been sitting in my garage for 10 years now. I decided, you know, that's a beautiful telescope. I've maybe used it 4 times. And I'm thinking, I'm getting older. I'm starting to push 70 now. I got to find a home for that telescope. And I immediately thought about UCONN and said, well, perhaps they can use it. So I made contact with UCONN and made some inquiries with the physics department to see if I could get the ball rolling and get that process started. That's when I met Dr. Wells and Dr. Matt Guthrie. Matt's sitting right over here next to us. And he came all the way out today to be here to be here for the talk with us. I cannot underestimate the value of Matt's contribution, or Dennis Perlott, who's sitting up here in front, wave that back there. Dennis and Matt put so many hours into this project, and it was all volunteer time. They spent hours and hours and hours of laborious efforts to make this old telescope come back to life. And couldn't have happened without them. So thank you, gentlemen. Very much appreciated, I'm sure, by everyone, including the students that are using it today.
Actually today.
Today.
Yep.
Oops, sorry.
Wow.
So this was our first trip out. Our first initial inspection. Head of the physics department called me up and said, you know, we already have a 16-inch telescope. Dr. Guthrie knows about it. Can you take a ride out with us and take a look at it? So that sounded like something we could do. And you can see it's in pretty rough shape. There's an old tractor parked out in front of it. It's covered with moss and trees are growing up everywhere. So not the best condition when we first found it. This is Dr. Wells walking around the front. We're trying to figure out how we're going to get inside there, and finally managed to get this rusty old door to open. I think it was 20 years, right, Matt? Dennis, what was the last log date?
2009 was the last log entry. So
2009. The dome is frozen and the slit's stuck or something, right? Yeah.
right.
So yeah, it had been closed for 20 plus years. So we finally got the door open. This is what we found. And I instantly recognized this Group 128 Cassegrain, classical Cassegrain telescope. It's a very nice telescope, originally designed and built by Cynthia Peters and her associate. It hadn't been moved in 20 years. So it was rusted in position, couldn't get it to move. Everything in the room looked like this. It was covered with mouse crap and leaves and sticks and nests. And it was really bad.
Yeah.
Wow.
So we're kind of just scoping out the scene here, seeing if it can be salvaged or not. That was really the first task for us was, yeah, can we save this old telescope or not? It had a nice ash dome, as you can see. It's an aluminum dome, so it's not a problem. It needs to be cleaned up. Not bad. This is the back of the telescope. They put a lot of old cobbled together counterweights on there to get things balanced. Focuser was kind of crude, yeah, and it wasn't even moving because it hadn't moved in 20 years. So, you know, we're taking a look at that. This is the position that it was frozen in. That red ascension shaft was locked. Turns out the clutch plate on the back of that shaft was rusted to the flange and wouldn't move. So I had to get up there and literally lean on it and pound on it to get it to break loose. Eventually we got it to move. And the deck shaft worked okay, but it was rusty and stiff, this one here. Well, we needed to check out the optics, so I needed to be able to turn the telescope down to do that. And I managed to get it a little crooked. You know, we got a little ladder over there and a chair. We climb up and take a look inside. And just generally checking out the pier, things around it, see all the debris that had accumulated on the top of that thing. A lot can happen in 20 years, and it's not good what happens. So this is what the front end, business end of the telescope looked like. The optics were completely corroded. The coatings were unsalvageable. This center stalk was rusted in position. This was a steel shaft, super heavy. 4-vane spider, not the best design for diffraction. It's they're 1/4-inch thick vanes too. You know, you should be about 5,000 or 6,000 some inches thick. So it was real kludgy, and it was not going to help the telescope perform well optically. So one of the first things we decided that whole system right there had to be replaced because it's not functional, too heavy, and it significantly impacts the optical performance of the telescope. So we thought about that. We'll go back here again. So once we made that initial assessment, we all got together, had a couple of meetings, and came up with this general statement of work and what we were hoping to accomplish. We wanted to clean and paint the observatory building, restore the telescope, of course, repair the observatory dome slit and rotation system. We found out that the dome was rusted shut, it wouldn't open. Either the slit or the rotation didn't work. We needed to redesign and fabricate a new secondary collimating system to make it easier to collimate. So I came up with a design for that. We'll get into that in a few minutes. And of course, we had to recoat the telescope optics. And Matt, in order to use it for students, wanted to make it a go-to telescope. And hopefully we could get internet access eventually to it and be able to open it and run the observatory remotely from the physics building. That was the ultimate goal. So these are some of the first steps for things that have to be done to be able to pull that off. We needed to clear some nearby trees and we had to widen the driveway and stuff. So that was pretty much what we were trying to do. Matt got us a whopping $2,000 budget to do all of that work. And the good news is, I think we came in at 1,980 something bucks, somewhere right in there at the end. Of course, a lot of it, I had stuff that we could donate, and of course, all the machining time and everything was just volunteer work for them. But I enjoyed every second of it. I'm sure Matt did as well. So I wanted to bring you back to this just to remind you what it was terrible about that secondary support system. First, those vanes are way too thick. They got to be 6,000 something inch steel, stainless preferably. And this whole center stalk is way too heavy. It adds so much extra weight on the back of the telescope and inertia. When you're trying to move something with big gears and make it a go-to system. You want to keep the inertia down as much as you can on the tube assembly. So that had to be redesigned. This was my first cut at it. Did a little sketch. How we're going to come up with a two-part secondary support system, and the whole secondary is going to be outside the tube, so we get to it. And there's going to be rods going down the side to the back to these little hand knobs in the back. While you did do the eyepiece, you can collimate the telescope. And you'll see that a little better when I get into some of the CAD modeling. So this is a section view of my first cut at the CAD model for that. Center stalk, this is where the secondary mirror is. This is the ring that's mounted inside the tube. This is the exterior ring. There are 3 spider vanes. If you ever build a telescope, Cassegrain, reflector, 3 spider vanes is the best you can do, because you're going to take half the diffraction from one of them, put it 180 degrees away, and you end up with 6 tiny little diffraction spikes instead of 4 gigantic searchlight beams coming off of Jupiter, which you don't want to see. So worked on the CAD model for about a week for those components. I want to just bring your attention. See these rods that go down? There's a little standoff right there, and it's got a threaded screw through it. And that threaded screw is threaded into this front piece. So when you turn it, it moves this in and out. So all 3 of those can move in and out independently, which means I can tip it or tilt it or move it in and out by making 1 rotation of each of those shafts. Ended up working out pretty well. Dick really liked it for collimating, Dick Parker. That's just a close-up view of what it looks like up in there.
Where are your centration adjustments?
The centration adjustments are right here. You see these slots? These pins, there's a bolt that runs through this surface that's a countersink. You can't see it in here, I didn't show it. And you loosen that, and that allows that to be free. And there's a bolt up here in the top that pushes down on the cross bolt, which allows you to pull tension and center the secondary in there. So I don't want to dwell too long on the technical specifics. I'd be happy to answer questions for anyone asks, because I got 127 slides. Oops, come on. So there's the whole tube assembly. First cut. Now, I haven't really done any work yet on the telescope, but we were kind of getting to the dome and some of the other tasks that need to be done. So when I first take the telescope apart, I always do this when I'm doing a restoration. Label every piece, lay it out on a table, give it a part number, and then I do a CAD model for it. So I end up with this when I'm done. And that tells me everything I know about how that telescope's put together. And it captures all the information about all the parts. And I make drawings for every one of the parts so they can be replicated should something ever break or they need to be replaced. You ship it off to machine shop, you get a new part made. That's what it looks like exploded. There's a lot of parts in that rear cell. You wouldn't think of it, but it really is. Finally got all of that work done. Got the tube model all finished, CAD models. Time to start working. So this is Dave Perry. He's an associate professor and he's like the go-to guy to get stuff fixed at UCONN in the physics department. Handles a lot of the facilities requirements and tools and anything else you need. Dave is the guy and he fixes stuff. So we got up there and we were evaluating the shutter and this thing was stuck over here on the side. See how filthy that is up in here underneath. West slit was stuck. This is a little wheel and there's a rail that rides on top of that and the door is going opposite direction. It's an ash dome. And on top of that track was sticks and acorns and mud and crud. That was so thick, right, Dennis? It was just, I mean, I was the guy that climbed up the ladder with the pressure washer to flush that out. And we all got soaked and covered with mud and crud. It was a miserable job. But we finally got it open. And because the first thing you have to do is get that slit open so you can see inside the building. It's pitch black in there, you know, in the middle of the day. So we got that open. Now here's Dennis. Dennis did so much work on this building. Half of the project literally was getting the building back in shape. And I gotta say, Dennis and Matt together, they put so much time and effort into that, getting that done. It looked like a brand new facility when we got it done. Oh, hours, weeks and weeks, just cleaning
Yeah,
and
probably
blasting,
about
crushing.
1,000 hours.
Yeah.
Over all the months. So,
Right, over many months.
Wow.
But there he is, getting the first coat of sealant on the concrete again. Hadn't been anything on it in 30 years. Oh, gotta go back one. So, all right, we gotta repair the dome rotation. Now that we got the slit to open, it's not spinning. And well, when we started to evaluate it, there's no wonder. The thing had a flat tire, had a big split in it, like right, the whole side was split open, rusted, completely frozen. So just to get those freaking bolts off of there was a chore. But we managed to get them off. And here's Dave pulling the split tire up, seeing what's going on with the drive system. Now this is a friction drive system. It's just a flat, slick tire. And there's a rail here you see behind it, runs all the way around the dome. And the tire just pushes up against that and it spins it like it's on a road. It's effective and it works very well. It works so much better now, right, Matt? That they put the abrasive paper on there?
It worked for about a year.
Yeah, yeah, right.
Now, is it manual? Do they have-
No, it's electric, but
but it was
last,
manual
what
Thursday
is it, a
night.
month ago, the motor burned out again.
Yeah.
So we need a new motor.
Yeah.
But anyway,
Are there ball bearings or what?
no, there are roller bearings. You can't see them. They're behind this, oops, sorry.
They're all around the dome.
They're all around the dome and they're wheels that are stood up on, little clevises and and then there's a flat rail on the upper part of the dome, rides on top of that. Anyway. So that's what the motor looked like. There were mouse nests in here and they were everywhere. In fact, we had snakes in the building because they were eating the mice. It was a good place for them. Yeah. So I finally got the motor off with Dave's help. And that's what it looked like in my shop. So it wasn't too bad, you know, it needed new bearings. So I had to take the whole thing apart. This is, you know, kind of what happens when you start getting into these projects. They kind of evolve and turn into monster things. So after this, you know, here we go. Anybody thinks I got an organized shop? Hasn't been there when I'm working. Yeah, everybody comes when I have it all nice and clean, polished up. But yeah, this part's everywhere at this point. And this is all just for the motor. So I put new bearings in it, put it all back together, got it all cleaned up, and it works. So it worked. And then I had to get this fixed and repainted. Getting out to a little more about the dome repair at this point. You can see all of this crud. It's like thick, ugly moss and mold, and it's stuck on everything. And this is what the scope looked like when we got it lined up, when we finally got it moved around. So at this point, we're working on the dome. You can see we did a little painting down here, and Dennis is doing a good job with all of that stuff. We got the scope moved back, so we know it'll move. But it's time to start working on it, cleaning up the scope and getting the scope going.
Okay.
This is probably a couple of months into it, so we have to take it apart.
Did you miss a video on that?
Did you want to play the video on this slide?
Did I miss it? I don't think I had one of that.
I
No, there was a little icon
Yeah.
on the bottom.
Yeah. No, we can skip that one
okay,
for sake of alacrity.
okay.
Sorry.
It's all right.
It was, yeah,
Yeah, that one.
Was that the
Oh,
door?
come on.
the dome rotation.
Yeah. Oh, that one.
Yeah.
Oh, you want to see that? Yeah. I
It's
do
up to
wanna-
you.
Yeah, let's start that,
Sure.
so. And then if you can get me back there afterward, that'd be great. So this is the first time the dome has moved in 20 years. Finally got it working.
We'll go
Time
back.
lapse over how many hours?
Yeah, it actually runs a lot smoother than that on the normal video, because we got the stream not too fast. Anyway,
Wow.
I love those old ash domes because they're the Palomar model. They look really slick. That particular model is $250,000 now, if you want to buy it.
Jeez.
Yeah, so they have another one on top of the physics building. They're gonna tear it apart and throw it. No, don't let them do it. Don't let them do it, man. That's a very valuable resource, and they don't go bad. You can fix whatever's wrong. All right, we're back. So, yeah, we're cleaning that up, starting to take stuff apart. These are big, heavy components. See how cruddy the tube looks. We had, see, I don't know those you know him, that's Francis O'Reilly back there, and a couple of the agro department guys were very helpful because the building is on the agricultural department land, and we need keys to their gates to get in, to have access to the building. So they're curious, what are we doing over here? And so, oh yeah, we're going to be opening up the observatory. They came by all the time, helped out, so that was good. Getting ready to pull the front ring off. Lots of screws. Paint's all chipped. Finally got the optics out and most of the guts in the rear cell. Time to pull the tube off the top. So that was kind of tricky. We got it off. Oops. Right there. Don't want to stay there. There we go. No. All right, there it is. So that's with the tube off it. Now this upper declination housing up here, that thing's got to be 300 pounds. You notice how it's it's got this odd bandit counterweight arm on here? That knocks it, you know, if I try to pick anything up here, it's just going to tip over and flip over. And so we had to figure that out, and figure out how we're going to get that thing off of there. And of course, most of the time it's just a hammer and start pounding because you don't have these tools right up here. There's a lock ring on there and it's got little slots in it, you know, and you got to whack it and whack it and whack it. Or you make a wrench. Well, I finally made a wrench, but it was 6 months later. So, yeah, a lot of pounding. Had to use the engine hoist to get it off. This is Dick Parker's engine hoist. He brought it up for us. This is the concrete stuff we actually used to do. You can see we're putting several coats in here. We're doing all these things simultaneously. So, let's go here. Come on.
That was my favorite.
Yeah, this is what it's like. That's 300 pounds easy sitting on the floor. We got it off, so at least we could get it sanded and painted. There's the shaft. That shaft is solid, and that by itself is probably 300 pounds. It weighs like well, maybe 150. So I don't think.
But still, it's
heavy. It is hefty, absolutely. It's got all these big threads down here on the end that you got to be careful of. You can't drop them, dig them, because if you bang up the threads, now you cut the threads on the lathe. So that's not good. So you got to make sure you protect all of that stuff. So we finally got it off. We got all of the components stripped off. That's just the RA housing sitting on the pier now at the end. And we're making some progress. That's the deck shaft on the floor. So here's Dennis. Attaboy Dennis. I said, Dennis was a hero in this project. He really tackled some of the big, difficult stuff like this.
Ooh.
How many days you spend stripping that off?
a couple. Yeah, that's in my garage.
It's in his garage.
Yeah.
And areas outside his backyard, getting it all cleaned up. Big part of getting everything restored is getting it stripped off and cleaned off. So he was tackling that. Same time, Matt was doing a lot of the assisting on that work as well. So here it is, about ready to be prepped for painting. Is the primary mirror. You notice that's a pretty good size central obstruction. And so I measured it's 5 1/4 inches. That's approximately 32% on a linear obstruction. So not drastic. And I was quite surprised it performed as well as it did. This is an F3 mirror, and it was good. Now, Group 128 telescopes have a reputation of being either very good or very bad. And UCONN lucked out with this one because it was pretty darn good. CCSU, Connecticut State Community College, has one of its twin sister to this, and the optics are terrible. You can't, it doesn't even focus. So, but look at some of the problems here that I noticed right away. You got, shoot, I'll show you here. It's in the back of my truck. You got 6 mirror clips, 3 times more clip diffraction than what you want to see. These are big, hefty honking clips too. So they're really, not only you got those big spider veins up in the front, but you got all this clip diffraction, which is killing the contrast in the optical system. So that had to be fixed. So redesigned that, worked on that. Oh, come on, back. There. That's the secondary mirror. It's pretty crummy. Oops. There was a lot of junk in there. See some fingerprints. This is actually looking through it to the back side. Those are fingerprints that somebody put on the coating in the back. It's just, it's terrible. You can see right through it. You see my face on the reflection right there? That's my face reflecting in the front, but you can see right through the thing. So the coatings were shot, absolutely shot. And you know, if we're gonna have them recoded, that's $1,000 for 16-set optics. We only got $2,000 for the whole budget, and 1,000 of it's gonna go on a control system for the computer, so that ain't happening. So, did any of you guys know about the new people using the silver coatings, the 2-part chemical silver systems? We bought that chemical kit. Matt picked it up, and in my garage, we recoated the optics. They come out pretty good. So here's the, look at all the moss and junk down here, right?
Took a shovel to
Big
get that
trees,
off.
yeah, you gotta scrape that off with a shovel. That's how bad it was. We still had the tractor there. Now, this is like 5 months after we started. Yeah, we'll get it out of there, we'll get it out of there. We heard that for 6 months, 7 months. It was always in the way. It's starting to look a little cleaner inside. We got a lot of clutter in there from working on it. Hey, a nice new tire with John Deere yellow paint job. Slick flat, and it actually works. Can we start that one? So this was the first time we fired this up. Oops, dang it, missed it. We gotta get back to it. We're going the wrong way.
Yeah, you think.
I think going the wrong way.
Yeah. There we go. There it is. So it's working. Yay. Actually can move the dome around now, which is a good thing.
Wow.
Yeah. Yeah, well, we were happy. I mean, that's a big step forward for us when we're dealing with it. All right, so let's go here. And it's, I think I'm going the wrong way. Yeah, I'm going. All right, so at the same time, we had to get some trees out of there because the trees were actually hitting the dome. So that was the first bunch of trees that had to go, because once you start turning the dome, these hinges catch the branches and they can bend it or twist. So we had to cut them, get all of that stuff, debris off of the building. But notice how much nicer it looks now that it's been coated, right? Yeah, nice job, then.
The tractor's out of there too,
Yeah,
nice.
tractor's out of there. It's all good. Looks nice and clean. That was probably late April.
That
Early May.
was probably October.
Yeah, that was definitely later.
Yeah, you're right.
Yeah.
Sorry. Thank you for that correction. It absolutely was. That didn't get done.
That might have been our opening night.
We could have been.
Yeah.
I think it was because the table was there with the sign on. Anyway, I'm getting into, so now we got to do some fabrication and testing. These are all the parts that I had to fabricate for that new collimation system. Built them in my machine shop. If I want to make spider veins, this is the way to do it. These things right here are not rivets. They're little drive screws. They look like rivets, but they're very long pitch screw, and it's like a sheet metal screw. You put it in, it's like a rivet, you tap it down, and it's like you rivet it in. So that holds all of that rod. I cut a slit in it. You know, you can see if it's a slit, cut it in up there. Drive it through, put all kinds of tension on it. Not gonna deflect it at all. Some of the standoffs with the bearings in there for the rods to turn the collimations, components. Oops. Dick made sure I put this one in. Said Dick did a lot of work testing and stuff, but I wasn't out there all summer, sweating like the rest of us. But he did manage to redesign and rebuild the primary baffle. And he was very proud of that, as he should be. That thing weighed about 3 ounces. And it was exactly the right shape for the light cone for the F3 system, as you would expect it to be when Dick Parker designed it. So that really improved the contrast looking through the telescope, because the center baffle was exactly just outboard of the image of the primary mirror when you look down through the optical system.
Oh, is that carbon fiber?
No, it's fiberglass.
Okay.
He made it out of fiberglass. Built it on a mandrel. Oop, back one. So here's what the inside the clutch plate looked like. Remember I told you that the clutch plate had rusted on it? That's the rusted clutch plate. Actually got corroded and stuck to that worm gear, so nothing could move. I finally broke it loose, and it was loose in this configuration. But there was an old worm gear drive, and that's what the worm gear drive looked like. I took those gears off and redesigned this whole assembly so that would work with the new go-to system. That's the new motors. Fortunately, I had the motors. I had 4 of them. So 2 of those RS servo motors went onto that drive system, and I had to figure out how to get it mounted on those blocks so that we could drive it with the timing belts. But you want to hit that one. There it is, finally running, first time. It's pretty cool.
Yeah.
That was a big day for me. Okay, you can kick that back out, please. And I'll go to the next one. And this is Matt's big contribution. He started very early on in the project, coordinating with all the sidereal technology stuff. We talked with Dan Gray, California. He owns that company. The sidereal technology controller, they have a canned system that you can buy for a go-to system. And it's about what, $800, $900, right, Matt? It was somewhere in that range.
That was 800 for the controller and then 100 for the handpad.
Right. So can we fire that one up? This is Matt. I don't know if the volume's on or not. You can hear him. No sound. So he's saying right now, let's go look at Neptune. And you watch now, both the motors are going to spin. And then they're going to center. And then this RA motor is going to start tracking.
Oh,
So how cool is that?
that's cool.
That is cool. So big day for Matt. Got that all done in his spare time between classes. Matt teaches astronomy at UCONN and physics.
I don't teach astronomy.
You don't? I thought you did.
I would like to.
Yeah. All right, next. So you teach physics for?
Physics for engineers
Okay.
and for non-science majors.
Right. So that was the worm gear before, you know, and I needed to make some new clutch plates for it because this clutch plate is not big enough. Doesn't provide enough torsional resistance, especially when you want to have a go-to system on there. So I needed bigger clutch plates. I had to machine those and make the clutch pads and everything else for that. And there it is, finally mounted in the system. The whole motor tucked right in there just perfectly, in fact.
What do you use for pads for the, on the clutch plate?
The clutch plate material is vinyl flooring.
Vinyl flooring.
Yeah, compresses very well, stays well in the compression, and works perfectly. Fortunately, I owe him a new one because one of them is cracked. And but it's still working, right? So don't fix it if it ain't broke. That's what I always say. Here's the beginnings of the fabrication of the new collimation system. So it's come along quite a ways. You can see those bolts in here that tighten it down. There's a, see that tiny little hole there? That's where the screw is that pulls it out, so you can tighten it up. That was first getting assembled. Come on. All right, so now we got to go into some fabrication and testing. So this is at Dick Parker's workshop. I had to pull the optics out, get them all checked out before they got coated. And we went, you know, could tell right away that needed, you've seen these already. So that's another shot of the terribly not clean mirror. Again, it's in rough shape. This is after I cleaned it. Obviously, it became obvious it needed to be recoated. However, good enough to do a autocollimation bench test on for the optical quality. So Dick tackled that, and we got it all set up. It just fit on his system just fine. Hard to see, but right in here, you see in the autocollimation lines from his screen, there is no edge issues. There's nice straight lines, and there's no turned edge. So it looks pretty darn good on the first cut. So I made notes of that, you know. Just a slight tear on the central hole, little tiny zone. Unless you've done this 1,000 times, you wouldn't even see it. It's just a hint of a little zone right there in the middle. Very minor. And no curvature at the edge indicated there was no turned edge on this mirror. So at f3 and 16 inches with no turned edge, that's pretty damn good. I was very impressed with that. So we made the assessment after that point. This was part of our report. Follow assessment indicates that the mirror wavefront error is approximately quarter wave. And there is a minor zonal defect at the 70% zone, nothing too meaningful. Mirror's edge is good. Both materials are zero door, very good. Expensive stuff. We recommended no rework of the primary because we were ready to refigure it if we had to. And that would have set it back months and months. But we made the assessment, it's good. No need to tackle that. All we got to do is get it coated. So I just captured all of the main specifications, the height, you know, the thickness, the weight, all of those types of parameters, just so they had them in their report. This is what it looked like when we started to strip the coating off. This is actually paper towels with ferric chloride on, it just drizzled on and it spreads out. And it don't take long. It'll strip that aluminum coating right off of that lickety split. So after we got it done, it's a little bit better. A lot nicer looking. Now that's silver and it's not perfect, but we did a pretty good job with it and it's working quite well right now still for $200 instead of $1,000. So there's the primary after that got done. Looks nice. There is reassembled with Dick's brand new primary baffle tube. Notice we only have 3 mirror clips now, and they're smaller. I had to make them thick enough to be able to withstand, obviously, the load and the weight on those corners right here. But they're pretty solid and more than adequate to do the job. Here's what the new tube assembly looks like, starting to come together now. I got the new secondary alignment system on the front. Notice how it's mostly outboard of the telescope. The optic is still inside the tube, but there are going to be rods that run down the tube here, and you'll be able to collimate while looking through the eyepiece, which is a big advantage for a Cassegrain telescope to be able to do that. There's just a closer view of the new collimating system. And here, we jumped ahead a little too quick. Here we are getting ready to get stuff put back together now. So restoring the pier and the housing, just a lot of paint, stripping, Dennis. In the middle of the summer, we're sweating our butts off in there, literally dripping because we're sweating so much. We got it all stripped off, cleaned up, repainted.
And painted official Husky blue.
We painted a big husky blue. That blue paint right there took 6 months to get. 1 gallon donated from the university. 6 months.
Wow.
Yeah,
We were 3 days away from going to Lowe's with a paint chip and saying, here, match this.
Yeah, match
Can't
this,
wait anymore, you know?
So yeah, that was really, folks, 6 months to get a gallon of paint. So here it is coming together. Starting to look a hell of a lot better than it did before. It's a lot happier now, that's for sure. Got the new RA drive system in, the first part of the go-to system on the RA axis. This is the tube assembly with the rods now. So you notice they run front to back. This is the lens cell, mirror cell side. This is the secondary support system I designed. You notice a little gap in between there. When you turn these rods, that screw turns and it moves this outer ring in and out. The nice thing about that is normally your collimating system on a secondary is as big as the secondary mirror. And you got screws behind it. And you got very low, just one thread on a 1032 screw on a fine pitch screw. And you turn that, you're moving it, shifting it quite a bit. When you move it out that far, it only moves a little bit when you move it 1/32 of an inch. So push that outboard and gives you better resolution and control of the collimation, and allows you, if you make one full turn of each of those, the whole thing just moves in and out without tipping. So you can adjust the separation between the primary and the secondary, which adjusts your back focus, which is important when you want to put cameras or different things back. So it was nice to have that capability. Not to mention, if you ask Dick Parker, you would track him down. Hey, how was collimating that Cassegrain? Did it in like 20 minutes. It's just, everything is just right there. You're looking right at it. It's just so easy to do. Where before it was, yeah, turn it another quarter turn. Oh, wrong way. And you got to communicate between two people, one up at the end of the ladder and one down at the eyepiece. Doesn't work very well. There it is, finally in the tube up there under the mount, and I had to come up with this little jig. This is a table that's sitting on a pneumatic table, so it's like a little jack table. I got, you sit there and it'll come up and down about 6-8 inches. So without that, we're not holding that thing up there, to do it. Putting the secondary in, finally getting that back in there. There's Matt making some fine adjustments to the counterweight system. We're checking balances at this point, because things change quite a bit, as you could imagine. But we're starting to get excited about it. It's, probably September by then, and things are getting real close to trying it.
Tuesday after Labor Day.
Yeah. Amazing that you remember that. I don't remember.
That's a good day it was.
Anyway, so it's starting to look like a beautiful scope again. That's a nice picture of it on a nice sunny day. One of the grad students out helping, doing some fine balancing. Do you know his name?
That's Kevin. Just know it was Kevin.
Kevin, right? So there's a lot of the grad students out there. In fact, you folks are going to be hearing a lot from Matt and Dennis and some of the people out at UCONN, because they've got a really good program that's starting to get developed out there. So he's going to be pretty well known in the amateur and professional communities in New England here pretty quickly. So just remember, you met him there first, because none of this would have happened without him calling to the university, talking to Barry and saying, hey, I've got a telescope I need to fix. So there it is, about ready to go. Looks a little better. I think so. Here's Matt getting ready. We're going to fire it up. I wish the sound worked on this, because this is so cool. Could you fire that one up, please? This is the first time the telescope moves. Any way you get that sound to work?
Yeah, I think I have to change a setting.
Yeah, just see if you can put it, you gotta hear it. There it is. That is so cool. Yeah, we'll let that recycle. Star in Draco, so we see a little more motion.
It's an echo in the dome.
Yeah.
Oh, my.
And it's So I said, show me, let me zoom in over here and show them what you're doing. They're back on Polaris, so that's just here. They're a big Polaris. Go to. There goes the scope.
Is that cool?
It's going to decide after a little while if it's going the wrong way and come back. Because it's smart. It should look pretty close to the park position. Perfect.
Nice job, Robbie.
Nice
That
job.
was a big day. We got that over. All right, back there. Okay, thank you. Yeah. So now we'll do a little bit of the before and after stuff, just so we get a direct comparison. So March and October, a little bit of different. That's many, many months in between. And just from another side, it's a beautiful facility. That was the one we saw earlier. And it was that dedication night because the table was there. That's the only time it was there. Pretty much, this had already been cleaned a couple of times by it. And the new system, just wrapping stuff up and getting ready to pull it all out, get ready to use it. And there's the scope from behind, beautiful telescope. If you get a chance to go out and look through it, every now and then Matt runs, a public thing, and it's worth going to see. Telescope is a spectacular telescope.
Al, did you have to do any fabrication for the focus, or was that serviceable?
I cleaned that up and we were able to use
The background music for this
Oh,
one
it was-
is Pink Floyd.
Dark Side of the Moon.
it. It was really good. Yeah, it was really good.
Crazy diamond.
Yeah. And there's one of the professional guys, images. So this is the first light ceremony. It was that night. We had a rededication for the observatory building. It used to be the East Road Observatory. And some of you folks here will know this person. But we had a pretty good turnout. A lot of the faculty was there from the physics department. And we had a little gathering, a little ceremony. Rededicate the telescope. It was rededicated for Cynthia Peterson.
Nice.
I knew Cynthia from the State Science Fair. We at ASGH, Scott and I, used to travel every year down to Quinnipiac and go judge the State Science Fair. And every year Cynthia was there to greet us. Big smile, happy to see us.
And I was lucky enough to have her as an instructor when I was an undergrad.
Right, right. So she built this telescope with, can't remember his name, but it was
Dick Mendeck.
a colleague of hers.
What year, Alvino?
69, I think it was.
70.
79, Yep.
79?
late 70s.
Okay. So we got it, oops, back, don't want to skip that. So this is Cynthia's granddaughter?
It's her daughter and
granddaughter.
Yep.
Celeste.
Who's also a professor, big surprise.
Yeah. Exactly. And here are some students out there looking through it.
That's
Too long.
Cynthia's granddaughter looking through it at Saturn.
Wow, Cynthia's granddaughter looking at Saturn.
Wow.
Pretty amazing.
Nice.
Nice picture. Beautiful. And now, today, people are out there, students are using it, taking photographs with it. And I think Matt did a fantastic job with the program. Thank you so much, Matt, for having me, letting me help you out with it.
Well, thank you.
It was very worthy project. No. And that concludes my presentation. Yep. There's nothing like hands-on. Yes.
So, how are you gonna use it with your students? What kind of projects have you got in mind?
So over the summer, we had a few engineering students who wanted to just get experience with a telescope and all of the just being around astronomy. We bought a little planetary imager, and took some images of the Ring Nebula and
Pretty decent.
N13. Yeah, they're okay, but they're a little out of focus, and tracking is a little bit. We have a polar misalignment, so if you take a long exposure, you get star trails. So we're still learning, but it was great to see the students figure out the software and how to stack, and we have some really nice footage of data actually coming in, which was very exciting. So that's what we're doing right now. I decided to prioritize eye to eyepiece viewing right now, and then at a later stage, we can do the research. And we're planning on doing exoplanet transits.
Nice.
We also
And
see
any of those
students gonna
know
do some
Bob?
research on star magnitudes. So
Any of those know Bob Horton, they do extrasolar planet transit work at Brown, so he's a good resource. And we know it's possible with these types of instruments. Yep. Well, everybody enjoy the rest of your AstroAssembly. I know I will. Thank you, Matt, for coming out. Thank you, Kevin.